recording also.
Good evening, all. Hope my voice is clear to everyone. Today, I will give a brief presentation on Rietveld refinement using GSAS-II software. Okay, so Rietveld refinement is basically a mathematical simulation of X-ray diffraction pattern or neutron diffraction pattern. Okay, so before going to the software analysis or an example, let me uh, give you some brief introduction about Rietveld refinement. So Rietveld refinement can be told like Rietveld refinement, analysis, or calculations. Okay, so it was initially introduced by Professor Hugo Rietveld on in 1963, and this paper, what I am given here in 1969 Journal of Applied Crystallography. So please go to this paper and read this paper to get the mathematical formulations, and it is very nice paper. Okay, so before starting refinement, I will share these two article, whatever I will given in the reference to you. So read this article, and this article also published in 1999, and it is basically gives the all form of guidelines we are using in GSAS-II or in other softwares like our PXRD in our institute, which is Rigaku made. So Rigaku has software like PDXL, so you can find Rietveld refinement software inside that PDXL, so you can use that also. But in our lab for a long time we are using general structure analysis software, so that is GSAS. Okay, so powder X-ray diffraction we actually use to characterize the polycrystalline samples. Okay, and from at the end, from after measurement, we get a one-dimensional XRD pattern, one-dimensional line, which in y-axis intensity given, and in in y-axis it is intensity, and x-axis is the 2 theta, that is the diffraction angle, or it can be d-spacing, or the q vector, that is momentum transfer vector. Okay, so it carries a lot of information about the material. Like from peak position, one can tell about the unit cell parameters like A, B, C, alpha, beta, gamma. Okay, so that depends upon the absorption and porosity of the material, the bulk material that you were using as sample in PXRD. Okay, so and it depends also some instrumental parameter like radiation, instrument and sample alignment, axial divergence of the beam. Okay, so from peak position depends on these 3 parameters. This is from the sample, sorry, this is from the crystal of the unit cell of the sample, and this is from the bulk of the sample, and this part is from the instrument. Okay, so if all 3 are correct, especially your sample property and instrumental parameter, you can calculate the unit cell parameters as well from the refinement. Okay, from peak intensity, one can tell about many atomic parameters. Okay, that like broadness or like peak distribution parameter and this thing. Okay, so this also depends on the sample as well as the instrument parameters. And peak shape, which tells about the crystallinity, disorders and defects. Okay, so actually what we see in from the one powder XRD pattern, these 3: peak position, peak intensity and peak shape. So we are blind to that. We don't know what is the unit cell parameters or the atomic parameters or these parameters. So to get into that, we need to refine the structure. Unlike single crystal XRD, where after measurement you will get a crystal information file. So there it contains all the parameters given here. Okay, but in case of PXRD, we only get ASCII file or line profile. Okay, so we refine, and for that Rietveld refinement is well-known simulation package. Okay, so to get accustomed with the powder extract measurements and the structural characteristics, please follow this book. Okay, so I don't have the soft copy of this book, but I'll, if I can collect, then I'll share with you. So the principle of Rietveld refinement method is based upon least square method. So least square method means here in this schematic I have shown that this red crosses are the experimental data. Okay, and using the unit cell parameters, what I have told earlier, this thing and the atomic parameters and the other parameters as a reference point. Okay, Rietveld refinement allows us to simulate or a duplicate pattern with uh, with respect to the experimental pattern. Okay, so and what we have to see, we have to see the difference is going down or not between the experimental point and the calculated point. Okay, so that can be given by a least square method, like here m is giving that figure. Okay, which is summation of weight, statistical weight of difference between observed point and the calculated point, where c is a constant. Okay, so our goal is to minimize this m, and these are the figures of merit, like profile residual. This is same thing, like m can be given as profile residual or weight profile residual using different formula. Okay, so all these parameters actually, if you follow this result of this parameter, the value of this parameter, you can uh, you can easily refine the, you can easily simulate the pattern. Okay, and the most convenient pattern and most useful pattern is the goodness of fit, which is the ratio between uh, weight profile residual and the expected profile residual. So a goodness of fit close to unity is the desired one. Okay, other than goodness of fit, one can follow weight profile residual, which needs to be as close to as zero. Then your you can find that your simulated pattern and the experimental pattern get converged. Okay, so Rietveld refinement is a iterative process, means after many iterations you can uh, converge the simulated peak to the experimental peak. Okay, and the software we use, as I told, that general structure analysis software with version 2. The version 2 has advantages, like it has a nice graphical user interface, so you can always interact with your outcome results and other things. Okay, so by simple typing GSAS-II, you can find this website, and from here you can download the software for Windows, Mac, or other systems. Okay, so and tutorials are also given, so follow this link. So with this brief introduction, I will show you an example, so that you can, it will be helpful for you, and it is really easy. Just stop me and ask me whenever it is required. Okay, so let me go to the software part. So up to till now, anyone has any question?
Yeah, what do different figures of merit represent?
Yes, here.
What do different figures of merit represent?
Okay, so these are different formula. Like, see, here it is giving the profile residual, means the residual when we consider the observed point and the calculated point. Okay,
Okay.
unlike in weight profile residual, you have to you have to consider the weight,
Statistical.
statistical weight.
Hmm.
Weight. Okay, in Bragg's residual, unlike the observed point, you are considering the Bragg intensity. Okay,
Okay.
and in expected profile residual, you are considering the number of parameters as well as the number of data points. Okay, and goodness of fit is representing a ratio between this and this. Okay, so the popular parameters is profile, sorry, weight profile residual and goodness of fit. These are also conveniently taken by in all manuscripts and other for communication. Okay, so goodness of fit needs to be close to 1 and weight profile as low as possible to 0. Okay.
0. Yes, sir. Thank you.
Rahul,
Yes.
if you say from the equation of goodness of fit, if RWP value is 0, then it is not possible to get the chi-square value, right? If we go theoretically RWP
Yes.
up to 0, then how we will get the value of chi-square? It will be 0 by something is infinity, right? So
0
I
by
think
something is infinity. No, one something by 0 is infinity. Okay, 0 by something is 0. So yes. Yes.
Yeah. So yeah, what I am saying, asking is that if like RWP and R experimental value are same, like it is not 0, but let's say RWP value and R experimental value are same, then also the fit is good, right? This is my question.
Yes.
Or is it
ratio
always
between
needed to become 0?
Weight profile residual, if it's close to 0 means it's good, means you the simulated pattern and experimental pattern is getting converged. Okay, towards it is going towards converge. Okay, so, and expected profile residual, what we are expecting. So these the ratio between weight profile residual and expected profile residual actually giving you that how far we are going towards the converge. Okay, so if the patterns are getting converged, then only your goodness of fit will be close to 1. Okay,
But yeah, in an idealistic case, for goodness of fit, why I observed, I mean, very idealistic. If this is the perfect fit or something, then shouldn't why I observed equal, why I calculated? I mean, the least error possible, right? That's what we want.
Yes,
so
yes,
the
yes.
numerator should go to 0, right? For each and every very idealistic case.
Yeah,
So
these should
square
go
will
to
become
0,
0.
but it can be given by this also. So these ratios need to be unity. Okay.
No, I mean, that is all right, but how do you explain from the first formula? Like, when y I observed equals y I calculated, how should I ideally expect pi square equal to 1 when it should go to 0, right?
Right.
So, what are we missing here?
I didn't get it.
I mean,
can you please repeat?
The numerator should go to 0 in a very idealistic case. Very idealistic.
Okay.
And in the same case, we require that chi-square should be equal to 1. But because the numerator is 2, chi-square will be 0.
Okay. So I think I have done some mistake. Okay. So this goodness of fit also by this formula, yeah, it in ideal case where there is convergence, okay, we will get a 0 value for chi-square. Okay, yeah, that's right.
We expect anything.
I'll get back to you with this. Okay, because
Okay.
exact mathematical formula I forgot. So somewhere I think I've iterated the same thing what is written in some literature.
Okay.
So maybe I was wrong.
Okay.
So yeah. So just comparing these two ratios, yes, you are right. Moglu is also right that if it is really converging, then it should go towards 0 and not unity. Okay. Right. So up to this, it is clear to everyone. Okay. So let me go to the example. Okay. So there is other mathematical formulations are given in this articles I have already cited. Okay. So please go through that, so you can better understand about the mathematics and how this simulation really goes. Okay, so please go through that article.
Okay.
So now, the, after successful installation of GSAS-II, you will get a desktop shortcut like this icon. Okay, so after double clicking or by just right click and run it, okay, uh, open it, then you will get this type of window. Okay, so it will show the some literature citation. Okay, and it will show these Python add-ons. Okay, so this need to be present in your system so that to run the GSAS-II software. If one of these 6 values are missing, then your this program will not run in your system. Okay, so make sure that Python is there in your system, and after completion this window, this is command from the window, so you can refine, you can do the simulation using this window as well if you know the Python coding. Okay, else there are other 2 window will pop up. Okay, these 2, so these are graphical user interface. So in one window you will see nothing, like it is a plot window with a plot. What plot will appear you can see in this window, and this is the main window where we will input data and will import data and export data. Okay, so let me show you an example with my own powder XRD pattern, one of my samples XRD pattern, that is. So first what we will do, before starting any simulation, just save the project. So going to file and then save project as. Okay, so I am saving project in desktop, like in a let me create a folder. It is test one. Okay, and the system I will do is lanthanum strontium doped lanthanum cobalt oxide. Okay, so that is the system. Then save it. Now your project will be created here. Okay, you can see from here. You can expand the thing. Okay, like here is a notebook. You can take a note. There is control. Like as I have said already that this simulation is an iterative simulation. You can lot of iteration will go on before getting converged. Okay, so cycle of iteration you can fix, like here 0 to 20 cycles are given. So 3 is by default given, 3 iteration cycle at one run. Okay, so we can increase if we minimize the time, and but it will also take much of your memory. So make sure that your system is good enough. So before giving more iteration cycle. So I'm fixing it to 3. What is the default? Okay, and covariance is where you can find the figure of merits. Okay, here the value of figure of merits. So then constant you can add. There are many constant crystal constants between 2 atoms and 2 adjacent atoms, basically to be depending on the distance. Okay, so constants are useful in case of single crystal or neutron diffraction analysis. Okay, for powder diffraction analysis, constants are not that much useful. Restraints are also given, rigid bodies and these things. Okay, so these are not that much useful in case of our systems. Okay, so let me import a powder XRD pattern. Okay, so powder XRD pattern needs to be in, like here import, then go to powder data. So powder data need to be like in Bruker raw file or a CIF file, that is crystal information file, or a foolproof, that is other software. Okay, GSAS file. So in this format it needs to be. Okay, So make sure that the data you have obtained from your XRD instrument, which is in this format. Okay, if it is not in this format, you just download a software which is named ConvertX. Okay, it convex, so it converts the XRD patterns. Okay, so here you can see the files to convert. Okay, so the files typically will get ASCII file. Okay, in our instrument, and then select file, and output file you can fix GSAS. Okay, and extension type will be raw, .raw. Okay, and then you can fix the anode and select the anode, and just after selecting the file you can do the conversion. Okay, I have already converted the XRT pattern what we obtained from Rigaku instrument. So let me import that pattern. So I'm importing the powder data here. So go to import, then powder data, and I'm selecting from GSAS powder data file. Okay, I have the file here. So yes, you can see the XRD file, which is, the format is type is raw. Okay, so I'm selecting this file, then go, and it will show like here file type is GSS powder data file. Then open it. Okay, window will pop up, which is this the file you want? Okay, so we have to make sure that this is the file, and just press yes. Then immediately another window will pop up that will ask you choose instrument parameter file. Okay, but in our XRD we don't get any instrument parameter file along with our measurement file. Okay, so here my suggestion is go with the default parameter file. Okay, so don't press open, just press cancel. When you cancel it, a window will come which will for like select default instrumental file. Okay, here many default instrument parameter files are given. So since our XRD has the source copper K alpha, so set the copper K alpha parameter file and press OK. And you can see that in another window why the plot will appear. Okay, and the data we have taken from 20 to 80 to theta angle. Okay, so let me expand this window. Here is the intensity and 2 theta. You can change it like other thing like Q or D. Okay, so D spacing or in the form of momentum transfer vector. Okay, this x-axis, or you can also change the intensity by square root of intensity or logarithmic intensity axis. Okay, so depending upon your requirement. So let it be here like this, so we can see whether what is going on in the plot. Okay, and if you look here in the project, another tree has come which is named with that phase or the XRT pattern. Okay, and it has comments. So there are comments which can appear. You can't edit here, and there is a limit. Limit is for the x-axis limit. Okay, you can make it like 50. I will define only for 50 to 70. So uh, it will take this much only. Okay, 50 to 70. But I want to refine the whole pattern. So I will take 20 to 80. 80 will not take, so 79.8 will take. So it will select whole pattern. Okay. Then important window option is the background. Since we are simulating the intensity, okay, as well as the peak positions and peak shapes, as I have mentioned in the PowerPoint file, that the parameters need to be simulated: peak position, peak intensity, and peak shape. Okay, so until and unless you subtract the background, you cannot get the right options. Okay, so right intensity you cannot have. So we have to correct the background, or we have to refine the background. So there are background correction, background refinement functions are there, many functions. So the popular one is the Chebyshev. Okay, so I will suggest that Chebyshev is the right choice for our for back Pentano type of detections. Okay, so our XRD, powder XRD has mainly two type of focusing, incident X-ray focusing. One is parallel beam, another is Bragg Bentono. Bragg Bentono supports the Chebyshev function for background correction. Okay, and for like log interpolate thing, this will suits with the parallel beam focusing. Okay, so for powder sample, just go with the Chebyshev function, and you can control the number of coefficient depending upon the how good is the straight, good the straightness of the pattern is. Okay, so this pattern is not straight pattern. Okay, there is the base, you can see the baseline here, it is intensity is higher while intensity is going down. So let me increase the coefficient to 10. Okay, then just refine it. Okay, right. Okay, so another thing that it is not getting refined. Before refining it, you have to, you need to have the standard profile or standard thing, because with respect to something we have to refine, but we haven't put anything till now. We only given the experimental data, but with respect to what it will simulate the calculated pattern. So for that, we need a standard XRD pattern. That is one drawback of Rietveld refinement. Okay, you need to have a standard pattern. So for standard pattern, you have to collect a standard .ci file of similar type of this crystal. Okay, having similar space group and these things. That prior knowledge you need to have before starting the Rietveld analysis. Okay, so for that you have to import phase. Okay, the standard, that is the standard. I'm going to phase and import from CIF file. You can import it from other type of functions as well. Okay, but that needs to be a standard one. Okay, or similar type of crystal structure. So let's import a CIF file. So here I have taken few CIF file. Okay, so let me take a wrong CIF file which does not meet, does not have the similar type of space group with the experimental pattern I have imported already. Okay, so this is not matching with my crystal structure. Okay, so after this window will appear, so you have to say yes here, and here you can write the name. So let me enter the name like lanthanum strontium cobalt oxide. So you have to select here like you want to add this standard pattern for a reference to simulate the calculated pattern. Then you have to check this box. Okay, and do okay. So now you can see a standard pattern is coming here. Okay, with options for
Rahul,
giving A, B, and C. Yes, sir.
can you just tell them that whether the standard pattern is fed inside the software, or they have to separately load it in the laptop?
Okay, yeah, that is an important point. So GSAS-II software does not have any standard pattern directory. Okay, but if you can use Foolproof or Topaz from Booker, that has inbuilt standard patterns. Or if you do the Rietveld refinement in PDXL given in the instrument computer in our XRD lab, there you can find the standard patterns. Okay, but here you cannot have. So GSAS don't have any standard directory. So you have to download the CI file. And for that, let me show you what you have to, you just Google it or go to internet and type crystallographic open, sorry, open database. Okay, so this is a free website from where you can download the zip file. Like this is the website crystallography open database. So you have to go to search, and you like it has many options by for input your demand or requirement. Okay, like COD ID, crystallography open database ID, or you can input another terms like text or like compound name or journal, yeah, or in which journal it get published, the standard pattern. Okay, volume and UI. The thing is actually helpful. Like you can input the element type. Like I have lanthanum, I have strontium. Okay, I have cobalt, and I have oxygen. So I'm giving in the input the name of the elements. Okay, so you can input eight up to 8 elements. Okay, if you but my compound has only 4 elements. Okay, so then just send it. It will take second, and you can find different compounds with that similar compositions. Okay, so here, but nothing is matching with, these are not matching with my expectation. Okay, so this is the type what I want. Okay, it has hexagonal crystal space group with rhombohedral space group, hexagonal type. Okay, so this type of composition actually I have in my sample, and I think, I hope this the one I have downloaded. Okay, so let me go back to the calculation. So that, sorry, let me show. After clicking here the CI file, this file will get downloaded. Here it got downloaded. Okay, so download is done. So you can take this CI file. So now let's get back to the software. So after importing the standard pattern, you can see the crystal structure, unit cell parameters. You can edit this manually. Okay, or you just by refining the structure, this will get altered. But you have the option to control whether you want to refine this or not. Okay, so see, like refine unit cell, there is a checkbox. If you check it, then the unit cell parameter will get refined after uh, after doing the refine option. Okay, so but if you do not want to refine right now, then you have to uncheck this refine unit cell checkbox. Okay, so where we was in the background. Okay, so by default, the coefficient will be like 3. Number of coefficient will be 3, and function is Chebyshev, and it is okay. So just do the refinement after checking the background function checkbox. Okay, and now this is appearing that it is getting refined, and see the RW is RW is the weight profile residual. Okay, so it is 17, and this pop-up window is telling that whether you want to load the new result. And see, your background line is coming, the red line. So see, the background is not matching, or it is not as per the expectation. Background should be like should follow the base of the experimental data, but it is like a straight line. So anyway, let accept the new result. Now, to get a better baseline, let increase the number coefficient. I'm increasing it to 10. So then do the refinement again. And see here the bending is coming and RW is going down from 17 to 16.8. So it is helpful. Okay. Now this is the background I got. Okay, I can increase it further to 20. So let's do the thing again. But look, it is not going much better. Okay, so it decreases by 0.2. So it almost converges with the background correction till now. Okay, so but and see the background is getting uh, deformed, so it is also not desired. So let's go back to 10. So and then refine, and it is coming like 16.83. Okay, so this is the background we have. So for right now, let's start with this background. Under the background, there is a option instrument parameters. So instrument parameters has in first step has source type. So we have source type copper K alpha. You select the copper K alpha. Okay. Other options are intensity ratio, zero correction, that is the source correction, this with the instrument. Okay, polarization correction, and other U, V, W, X, Y, Z. These parameters belongs to Gaussian and Lorentzian coefficient correction, and especially these six parameter, these three U, V, W controls the shape of the peak, while X, Y, Z also these are the Lorentzian coefficient also uh, yes, regulates the shape of the simulated pattern. Okay, so importantly, these six parameter we will refine after refining the unit cell. Okay, and there is another option, that is ASH by L. So this is a need. We don't need this refinement, because these are helpful when there are multiple optics used in diffraction measurement, like in case of synchrotron. So synchrotron XRD, they have to use multiple optics. So for that, you have to correct the slit width of the sample as well as the source. So sample and detector, and the radius of the goniometer. Okay, so this is related to the optics alignment. So for normal powder XRD, you don't have to refine this SH by L. So as I told that before going to instrumental correction or refinement, first you have to do the unit cell refinement, and that you can only do after going to this case tab. Okay, so here in this option, we have already seen that there is unit cell parameters we can refine. Okay, in another tab there is data. Data is it shows the trace fraction. Okay, the size. Okay, micro strain, if your sample is micro strain, and this thing. So these are the parameters we after getting a good converging simulated pattern, then after we will refine this thing. Okay, so these are not primary parameter for refinement, but if to refine, the primary thing to refine is the unit cell. Okay, and most importantly, we have to see the composition of the standard pattern. The atoms are like given here. Let me expand this window. Okay, the atoms presents are here like lanthanum, cobalt, oxygen, but strontium is not present here in the standard pattern. So what we have to do, we have to incorporate the strontium in the unit cell atom list. Okay, and here the type of atoms are given. This is the name of atom and this is the type of atom. You can change the type of atom. Like here, lanthanum is given. It is like no ionic charge is given here. So just double click here. There will periodic table will pop up. Okay. So from you can select, you can go to lanthanum and you can change it from lanthanum atomic to lanthanum ionic lanthanum. Okay. So it will, so like La3 plus. Okay. And when you change, a unit cell will show here, which will which will, from where you can track that whether the atom has changed or not. But since we haven't changed any atom type, okay, the type is same, but we have incorporated the ionic charge, so it will not change that much. Okay, so we cannot see the change here. So let's change the other type, like lanthanum 0 to 3, cobalt. Cobalt present in this material in +3 generally. So cobalt is also +3, and all oxygen should be in 2 minus. So they are oxide. Okay, so now the name of the atoms are given. So these are the general name, like the La1. You can change it like A, B, C, D. Okay, so no problem. But type, here you need to be cautious. Okay, so other than the type, there is columns like X, Y, Z. These are denoting the positions or the coordinate of the particular uh, ion or atom. Okay, so here lanthanum has coordinates like this, X and Y and Z, and another parameter is the fraction. So in this site, lanthanum is fully occupied, 100%. Okay, so one fraction is 1. We can change the fraction, like we have doped strontium in the lanthanum side, so we will change the fraction, like we have doped lanthanum by 30%. So let change it to 0.7, because lanthanum has now only 0.7 fraction in that particular site. Okay, we have replaced by strontium, other 30%. So to incorporate the strontium in this list, just select the atom where you have incorporated strontium. So we have incorporated strontium in lanthanum side, but lanthanum is present in two sides of a single unit cell. Okay, so in both sides we have to incorporate strontium. So select the lanthanum, then go to edit atom and just click append atom. So one atom, unknown atom will appear here with type hydrogen as default. Okay, so just change it to strontium, strontium 2 plus. Okay, so we have doped lanthanum with strontium 2 plus, and the coordinate will be similar like the lanthanum. So now here we are replacing 30% of this lanthanum, lanthanum 1. So coordinate needs to be exactly similar. Okay, so coordinate x is 0.74991, and it is y is 0.74987, 0.74980. Okay, so and the fraction will be 0.3. So now this side, this particular coordinate is filled by 30% strontium. Yes.
Here you have two time of lanthanum, right? Like first
Yeah.
two. So which
Yeah.
coordination will you choose? Means like here you have
In
choose the first.
we don't know that we just during synthesis we just put 30% strontium in place of lanthanum. Okay, so we replace the lanthanum with 30% strontium. So we have to incorporate 30% strontium in both sides. So this is in this strontium 11 is getting incorporated at the lanthanum 1 side. Now another atom we have to add in place of this lanthanum. Okay, so see the coordinate. By following coordinate, you can easily tell that in which side this strontium is going. So this coordinate is 0.74991. So this lanthanum, it is going to this lanthanum side. Okay, it is replacing this lanthanum. And
another question.
another one I am adding over here. So this is strontium 2. So it will go to lanthanum 2 side. Okay. So here it will be 0.25009, 0.25014. 021, and the fraction will be 0.3. So this side has 0.3 strontium, this coordinated 0.3 strontium and 0.7 lanthanum. Okay, so this side is fully occupied. Now you can incorporate oxygen vacancy using the following, using the similar method. Like if you want to make oxygen vacancy at particular site, let's say at this coordinate, you don't know which oxygen atom is this. Okay, so for that you have to follow the here. So you can change the drawing options, like draw atoms, fallen state. Okay, so see, so this is the A, B, and C. Okay, axis. So just this oxygen is 0.25x. So most probably this one. Okay, 0.25x, and B 0.8, and here 0.6. Okay, so this oxygen. So here, if you want to make vacancy here, okay, just in case of occupancy side, that is the fractional side, just reduce the fraction, like 0.9. If you write 0.9, that means you have incorporated 10% vacancy here. Okay, you are not giving any replacement in this coordinate, just having a vacant 0.1 fraction. Understood?
Well, the
So
one question.
yes.
Can you show in the model that? Hello.
Hello.
Can you show all the different types of atom? Like here, it has 2 types of lanthanum, 2 types of cobalt, and most probably 6 or 7 type of oxygen. 6 types. So in the model,
Okay.
how are you
here,
saying it is 6 type of oxygen? Okay,
yeah.
just numbering, right?
Just numbering, yeah, because it is 6 type, because see, one asymmetry is there. Okay, if it is symmetric, then it will be like a 1 type. Okay, so in this particular space group, okay, what we have used in the standard pattern has these many different atoms in per unit cell. Okay, this could be much simpler if you use another space group. Okay, so I will show that. I will show you that. Okay, so just for the sake of example, let me start with this composition. Okay, we don't know whether this is the perfect one or yes.
You
Yes.
have incorporated in one oxygen 10% vacancy. Okay,
Yes.
so to balance the charge, the metal oxidation states also will change, but we cannot.
Yes.
So how
Definitely.
means like, yeah, so how
Definitely.
like 3 plus 2 plus, these are the general oxidation states of usual oxidation states of lanthanum, strontium, cobalt. But when
Right.
we are incorporating oxygen vacancy, so this charge will be reduced, right? So how to do that?
Okay, so see, the parent composition is like lanthanum, cobalt, oxygen. I have doped strontium in lanthanum side, but see, the strontium has +2 oxidation state, which is going into the lanthanum, which has +3 oxidation state. So it is reducing the cationic charge as well. Okay, So that's why oxygen vacancy is a consequence of the reduction in the cationic charge.
Okay, okay.
So it is a result
Means
of
as you are
reduction in the
giving a
cationic charge.
+2 charge, that's why you are reducing the oxygen atom.
Yeah. Yes. So,
But
and that
all
is
time,
experimentally. Yes.
but all time, like sometimes, like there are mixed valency of one material only. Okay.
Yes.
Or some same valent compound are introduced but at a less amount, so that the total charge is less than, suppose cobalt 3 and cobalt 2 are present simultaneously. Okay, but due to +2 state, the means same element is present but in two different oxidation state. Okay, and due to that there are some oxygen vacancy or
Yeah, I got your point. So that is the thing we have to play with. Okay, we have to play with the fractions and the charges here. Okay, to get and the refinement, the figure of merits will tell you that whether you are going in right direction or not. Okay, but the suggestion is that commenting on such a tiny fraction of oxygen vacancy and this thing, those cannot be uh, accurately accurately said from XRD. Okay, you cannot say from powder XRD. For that, you have to go for neutron diffraction or synchrotron XRD. So, for sake of example, or to prove our claim, you can always do the fractional change here, but for tiny fractional change will not be taken care by the Rietveld refinement. Okay, uh, so and what you have told, that the multivalent ion of the same element, okay, can make oxygen vacancy as well. So for that, you have to incorporate and you have to play with it to see whether that by incorporating the oxygen vacancy actually helping or not. So am I clear, Sonat?
Yes.
Okay. So with having this type of composition and fractions, let me start the refinement. Okay. So I'm going to general tab. So where you will find the window to refine the unit cell. Just check this box and do the refinement. See, the weight percent, the residual gone down from 16.8 to 15.3, and that is because you can notice here the green line, that is the simulated line, and the blue marks are for experimental line. So now simulated pattern is gradually coming. So let do one iterate the process and see it is going down. Okay, so it is not converged yet. So go for one more round. Sorry. Or you can increase the cycle of iteration. So I'm increasing to 10. Okay, now refining. So at a time, instead of 3, it will take 10 cycle of refinement. Okay. So now you can see that the simulated pattern is coming in place of on the experimental pattern. Okay, but it has many peaks and it is not as the step like the experimental pattern. Okay, so before going to that, let's do another refine cycle with the unit cell refinement, whether it is changing or not. Yeah, there is a change, but it is very small change. Yes, it significantly changed from 7.6 to 5.8. So it's fair enough. Do another cycle of refinement. Yeah, see, it's how nicely the simulated pattern is falling over the experimental pattern. Okay, but there is no such big change in the residual. Okay, so let's stop the refinement here, the unit cell refinement. Now go back to instrument parameters. Since we have already the simulated patterns, okay, so now correct the instrumental factors like intensity ratio and zero correction and the polarization correction, and do the check the boxes and start refine. It will uh, do the instrumental correction. Okay, so the small amount of residual gone down. Next, do the U, P, and W correction. So is a coagulative function coefficient. These coefficients belongs to coagulative function which controls the shape of the peak. Okay, so U, B, and W I have selected all together and do the refinement.
Is that Sudipto? Just can you mute your microphone?
So now see it's
And you must
significantly
say,
gone
Rahul,
down.
that
Uh,
these are basically the pseudo-void shapes. These are not the Lorentzian or
Yeah,
Gaussian.
yeah, yeah, definitely, definitely, and it is important. So the simulation is based on the pseudo-void function. Okay, so not predominantly Gaussian or Lorentzian type. So it's a mixed Gaussian and Lorentzian. Okay, so you can see from here there is a mixed Gaussian and Lorentzian factor. Okay, so it is a pseudo-void type, and that is fair enough for doing the powder extent refinement. Okay, so I have done with the UBW refinement. Then I'm going to XYG refinement. Okay, so after refining, let's see, it is initially 2.3. Now whether it is changing or not, residual. So always these residual tells us the all the time that whether we are going in right direction or wrong direction, whether the incorporation of vacancy or changing atom is correct or not. Okay, so we can follow the residual. We have to minimize the residual. That is our main goal. So let's see the whole graph. Okay, so it's fair enough. Here see the residual. This is the cyan color line is the residual line, and it is for pretty good. Okay, but if you closely look in every peak, this is not fitted well. Okay, at lower to theta angle. So there is some problem. Okay, another thing I'm expanding here. Here is another peak which is not fitted. Here no peak is simulated peak is coming. So from prior knowledge, we have already known, it is known to us that this peak is for cobalt oxide impurity. So we have cobalt oxide impurity in our sample, and this is another impurity. So we have to take care about all the peaks. Okay, so and see, just by doing the parent lanthanum cobalt oxide without caring about the impurities, we have achieved weight residual up to as minimum as 2.2. So from here you can publish it. Okay, you can report it, but that will not be fair enough. And goodness of fit, which is also good, less than 5, 4.77, that is also good enough. But we know by seeing by looking at the peak fitting that it is not fitted completely. Okay, there are impurities, we have to take care about them, or there is some peaks which are not fitted well, so we have to take care all the things. So for that you have to go one by one, and manually or single refinement you can change the fitting, or you can get better fit. Okay, so that is that is you have to do, because you know your system better than uh, anyone. So that is one factor. Then for better fitting, you have to do by your own experience and with prior knowledge on the system. Okay, so up to here I am done with the fitting of lanthanum, strontium, cobalt oxide. Okay, and there are impurity phases like cobalt oxide. Let me show you how to refine the impurity phase. Okay, so but to mention here that I'm not complete with the refinement here, so that will take time. So in this short time it is not possible to get good fitting, but for the sake of giving an example, it is I think it will be fair enough for you to start the refinement. And in next step, let me show you how to incorporate secondary phase, that is the impurity phase. Okay, for that you have to just go to import and add another phase from zip file, and I have already loaded that phase like here. So the impurity, I know that this impurity is coming from the cobalt oxide, and see I have already have the cobalt oxide impurity standard pattern, cobalt oxide standard pattern. So just let me incorporate this one. So I am now introducing a secondary phase. So I am checking that yes, I want to take this phase for refinement and pressing OK. Okay. Then my suggestion is when you want to do the refinement against cobalt oxide, just uncheck the refinement for the lanthanum strontium oxide, the phase 1. Okay, because we have already refined that phase. So better to let it be like it was. Okay, then go to cobalt oxide and please uncheck all the box in instrument parameter. Okay, and sample parameters. So instead of histogram scale factor, that is okay. Background correction factor will be checked all the time, and if you see that backgrounds is fine, then you can uncheck it. Okay, but my suggestion is keep it checked, because all the time background will get modulated with the refinement. Okay, so let's go to the cobalt oxide phase and check the refine unit cell. Okay, then press refine. See, the RW is going up and all the pre-simulated peaks has gone down. Okay, that is because we are not taking care about the phase 1, which we have already unchecked. We have taken care only the cobalt oxide phase, which is newly incorporated. Okay, so just press that we want to load the new result. So now I will tell you that how to get back the, where it is, yeah. Okay, how to get back the fitted pattern for phase 1, that is lanthanum strontium cobalt dioxide. For that we have to take care about the phase fraction. We haven't yet taken care about the phase fraction. Cobalt dioxide is the impurity phase. That means it has very small fraction, okay, in the sample. So just check the phase fraction in data box, okay, data tab. Then do the refinement again. Now see, it is going, the peaks are getting back to its own positions. Okay, and shape is also good, and residual is also good. It is coming below 2.4. Now it is 2.1. So, and here, so refinement done, and let's check whether impurity phase is, yeah. So in cobalt dioxide, there is PChem, and this is also a cobalt dioxide peak. Here also the peak appeared. Okay, but here is another impurity. So I'm not taking care about that right now for this example. So I have the pattern sample. So this is palladium oxide impurity. So, but by this example, I have shown you that how to refine crystal structure, okay, using a standard pattern which you have to download from internet, okay, and you can certainly change the atoms, fractions, atom coordinates for better refinement, okay, that you have to take care by your own, okay, and that will time consuming process. And in next step I have shown you uh, how to incorporate the secondary phase to and refine the secondary phase and to get a combined simulation uh, pattern. Okay, so after, if you are uh, satisfied with the simulation, and in that step you can export the whole project as crystallographic information file. Okay, so crystal information file. Okay, so you can save it, you can give the instrument name which are required. So just write the instrument name. The radii you can change if you want. So you have to write your name where and the create CIF. So CIF file is the file from where you can extract all the things what we have refined here. Okay, so that is a small notepad file. So you can you can take that for a three-dimensional visualization using different softwares like Vista. Okay, so up to here, I have done with the simulation, and all the simulation have done. You can find it like from desktop where we have opened the folder here. So at any stage, so these are the with time the different files have has been created. Okay, so from here you can also get at which step you have done what. Okay, so these are also useful, and this is the CI file generated, and this is the list file that contains all the parameters and other things. You can extract it from here. Yes, so I am done with the simulation example. So anyone, if anyone have any question, please you can ask.
Rahul da.
Yes.
Rahul da.
Yes. Santanu.
Rahul da, can you explain again the phase fraction?
Okay, phase fraction. Okay, that is important. And phase fraction is like see, when you are giving command that do the simulation using a particular phase, okay,
Yes.
it will take that it is the sole phase present in the sample. Okay, so maximum intensity is coming from that phase only, it will take. But what happens, see, the fraction of cobalt dioxide present in the sample is not equal to the fraction of lanthanum strontium cobalt dioxide phase. Okay, the perovskite phase has the maximum phase. That's why you have obtained maximum intensity for the perovskite, while cobalt dioxide has small intensity. So for that, you have to refine that phase, that how much carbon dioxide is there and how much perovskite is there. You have to check the phase fraction and see by default the phase fraction is 1, but after refining, see the perovskite, I've selected the perovskite phase here, which came to 95.78%, while cobalt dioxide has the rest of 4.3%. Okay.
Okay.
So it is after simulation, after refinement we have obtained. Okay, so that's why the intensity now gone down for cobalt dioxide. It will take automatically. Okay, it will calculate the weight fraction as per intensity and volume of the area of the line. Okay.
Rahul,
Yes. Mm.
go to the coordination section. Atom.
Atom. Okay. So
Yes.
perovskite, yes.
Oh yes. So like sometime in case of your doping, you are changing the fraction. In which case
Yes.
the XYZ can be changed and how it can be changed. Because in case of
Yeah.
ABC parameter, there is an option for refinement of ABC. But how we
Yes.
will do in case of the coordination?
Yes. So sometime you see that for your experimental, like this intensity is going up and this is going down. Okay.
Mm.
This is in ideal case, this is the maximum intensity, this plane. It is 112 plane. Uh, Here reflection list is here. Okay, so see, I've selected the perovskite and check this peak corresponds to this plane. 0, 1 minus 1, 0, 1 0 minus 1, 1 minus 1 0. Okay, this plane. So let me zoom it. Yeah, so this is mainly because of 112 plane. Okay, so initially it was showing wrong thing. Okay, so now it is showing the right one. So this peak corresponds to these three reflection: 112, 121, and 211. Okay, so uh, if in any case you have you find that this, instead of this 112 peak, this 100 peak is maximum peak, then you have to take care about the atomic arrangements, like where is the atom here. uh, okay, so this is the atom. Let me show you that 112 plane and show the plane. So this is the atomic plane where lanthanum and cobalt is present in the plane. Okay. If you change the coordinate, the atom will shift from its
Plane.
own position. Okay. Own plane, own position. So, and that will result the alteration in the reflection intensity, because reflection is coming from the atoms. Okay, so if atom is getting shifted, if it is going here to here, see what will happen. Let me change the position. This is the lanthanum atom. Okay, lanthanum, and this is lanthanum. This atom. Okay, so I'm changing it from 0.252 in x-axis. Let me change it to 0.5. I've shifted. Now I'm refining it. What will happen? Just see intensity here a new peak is coming. Okay, so you have to take care about the, you have to refine the atomic positions, the atomic coordinates, to get the actual thing. Okay, so reflection will change, but this is the coordinates what we obtain from the standard pattern, that may not be the same for your own system. Okay, so you have to refine this fraction. Like you can refine it automatically by giving command to the software, like I want to refine the coordinate here. Okay,
How did
okay,
you
that
get
I
this
have got
option of
from,
roll?
see, refine,
Achha,
double click
okay.
here. Okay, coordinate. Okay, so now refine it, but what will happen, let me show you. Okay, so it will automatically refine the coordinates, but all the time it is not fruitful. Okay, you have to do manually, and my suggestion is do the if you want to change the coordinate by tiny amount, not by so high amount. Okay, like here it was 0.25. Okay, so do by manual. Okay, do it manually. That will be helpful, because you will have the record from where to where you have changed. Okay. Yes, I have. So Muglu, it is clear.
Yes, yes. Thank you.
Rahul, visual
Mhm.
because sorry, I'm saying that in the phase fraction,
Yes.
like CO3O4, where
Mm.
the phase fraction. Yes. So after refinement, the value has been changed automatically, or we have to give the phase fraction for the refinement.
No, we are refining. We are giving command to the software to do the refinement against phase fraction. Okay, so it is refining the phase fraction, and that's how it automatically generating the area under the peak. Okay, so it has the area under this peak and area under all the peaks of corresponding to LSCP, perovskite and cobalt dioxide to keep the weight fraction.
Okay.
And then it has the knowledge about the molecular weight and other things. So from where it is calculating the weight fractions. Okay.
Okay.
Because in general tab you can find what is there, ABC, volume, alpha, beta, gamma, then its density, all kind of things. Okay, here the different atomic parameters. So you can find the molecular weight of that particular fraction. Okay.
Okay.
Rahul,
Yes.
for the amorphous system, the noise or the background noise is more for that system. So that case, the Rietveld analysis can we do?
Amorphous for information amorphous system will not give you the reflections. Means you cannot, means for highly polycrystalline system or amorphous system you cannot have the extended pattern. No? It is better to have as many as reflections to get better refinement. But for highly polycrystalline sample where the pre-broadness is much higher, there also you can do the Rietveld refinement. Okay,
Rahul, I think
it will take
Rahul,
the step.
what he's asking is that if it's amorphous, partly amorphous, so in
Okay.
that case the background will be very large.
Yes.
So if the background is huge, how to take care of the fitting? That's what he wants.
Yeah, one perform the refinement, but the problem is reliability on that simulation. Economy as reflections, but in partly amorphous, many reflections are not present, only few reflections with broad fix. But yeah, you can refine it, no problem, and you can have the CI file as well. But that may not be the actual crystal structure for that sample. Okay, so better to have uh, at least good reflections, as many as possible. But people show on that samples also. Yes.
In the CI file, for standard CI file, all the planes are present, all the planes.
Yes.
But in our system, some planes are missing. So for that case,
some planes are missing. So
or
it
intensity is very low. We did not.
Okay, so it is plane dependent growth, means it is growing in with a particular plane, along particular plane. So that's why it is giving maximum peak, maximum intensity at some place, or the maximum in standard and your experimental pattern. Whether Anil,
Yes.
hello, the
Yes.
maximum, the 100%
Yeah,
100%
100% peak is
intensity.
present.
Okay. Others are not.
But the other
Yeah,
peak,
that is fine. That is fine. For that, it you can refine it. No problem.
Okay.
at least intensity ratio should be maintained, else your crystal structure is changing. Okay, it is changed, means it is not the exact crystal structure as like the standard pattern. Okay, like here I have the maximum intensity at 32 and the next intensity is 48. Okay, so that should be maintained in standard pattern as well as in experimental pattern as well. Okay, if this intensity is higher and this is lower, then that is not the case, means that is not the same space group or crystal structure like the standard pattern. Okay,
Okay.
so then you have to change the space group or crystal standard pattern.
Right,
Okay,
Rahul,
yes.
who is that? Any other question?
Rahul, okay, one second. Like for which system we cannot do refinement? Like if we don't have the CIF file idea or let's say less HKL value, and what if there are some other system which we cannot do refinement next.
So standard pattern, if you don't have, you have to simulate it. Means computationally, like you have to start with some standard file. So that you can generate from ab initio method, but better to have experimental standard file like single crystal CI file. So yeah, you can generate standard file from ab initio calculation. Okay, or that is one case. Yeah, if you don't find any standard files, and in case of means when we cannot do the Rietveld refinement, when your data is taken with the data interval more than 0.02. Okay, so in that case Rietveld refinement will not be reliable. You can refine it still, but data refinement results will not be reliable, and your signal to noise ratio need to be as low as possible. So with lower signal to noise ratio, you cannot refine.
Okay. Okay. And is there other search engine than crystallographic database means to search?
Yes, there are
CIF?
many from
Means,
NIMS. One is there NIMS MIT
there are
collaboration has some.
search engine, but these are actually licensed, so it's free.
No, it is free.
Okay.
I have the thing, so I can share with you. Okay, and there is like materials project, American Materials Society, like there that is paid, but materials project is free, and NIMS project is also free.
Okay. Thank you.
Anyone else?
Okay.
Okay, Rahul, I think that very good. It's wonderful that you have explained it so well. I think that one more session will be important to have where basically how to export the output, into the Vesta software, and how to create the 3D structures, how to find out the bond angle, bond lengths, and the other things. What are the basic things? So you can basically take the simplest, like the system that you took today, this ALSCO, right?
Yes.
So similar system you can take, and taking that example, you can basically say it again. I think better do it next week. Okay. So
Yeah,
you
next
have,
week is better.
yeah. So you have basically explained all the things. Now it is very much important that to take one system, like that day Shahnaz was saying that nickel oxide is a very simple system. So so to practice this, so I think Sonu will share this one with everybody. So you will have that, you have to go through it, and then maybe nickel oxide, maybe zinc oxide, the simplest systems. Okay.
Yes,
take
yes, yes.
them from our the soft data that we have. All of you, I and must try to fit that on your own. Okay, and if you try to fit it, and if you find any kind of difficulties, you write to Rahul. Okay, separately, and then you can basically suggest them that what to do, what not to do, but you have to give a try. You have to start with somewhere. So all of you, it is very much important to do this. And but after the next week, when you explain about the Vesta and the important things, the weight fraction of phase 2, and maybe phase 3 can also be there, like as you said that you are not doing it, palladium oxide is there. So different phases can be put in, but there are a lot of other things also. So next week also you say something about this. Okay, it may not be too lengthy, but somewhat it should be there. But all of you must practice it, and I want to see that you have done that. You have tried the fitting, you have understood the fitting, because just listening to this and just keeping quiet will not help you anyway, because all of you need to do this at one point or the other. And always remember that we don't have very sophisticated instrumentation. For example, XAPS, whatever Vishwadeepa was showing, and the other things where we can get the lattice, the positions, or the oxidation states, or the things. So we rely on the XRD